Hi everyone, I'm Mingquan Xu, and I'm going to introduce my work on Quartz Superoptimization of quantum circuits. So quantum computing is a new area, and the computation is represented by quantum circuits. This is an example of a quantum circuit. You can see that there are 2 qubits, and there's a U1 quantum gate followed by a U2 quantum gate on the first qubit. There are also 2 single qubit gates on the second qubit. After these 4 gates, there are 2 2-qubit gates called C0 in this circuit. It turns out that we can actually optimize this circuit into a circuit with only 2 gates. The smaller circuit runs faster with a lower error rate while doing the same computation. So this is a general motivation of quantum circuit optimization. Existing quantum circuit optimization approaches are rule-based, and they manually design circuit transformations. They usually use heuristics to optimize. For example, greedy transform the circuit towards fewer gates. The figures below show 2 examples of the manually designed circuit transformations. And there's a challenge here. Different quantum machines can have different gate sets, and the circuits can be quite different. For example, if the gate set of the quantum machine on the left is U1, U2, U3, and C0, then the circuit looks like this. However, if the gate set of the quantum machine on the right is H, X, RZ, T, and C0, then the circuit becomes the one on the right. In classical computing, the analog is different ISAs. So with existing approaches, you need to manually design transformations for each gate set. Because you are doing this manually, it involves a lot of efforts, and it also raises questions like if you are missing any optimizations, or if the manually designed transformations are correct. In Quartz, our idea is to automatically generate circuit transformations and use cost-based backtracking search to optimize. So why this is a good idea? First, it's universal that it works for all gate sets. And it requires less engineering effort because there's no need to design circuit transformations for each gate set. And it also leads to better performance, and that it matches or surpasses Pentium optimizers. We also have our transformations verified, so it also guarantees correctness. Let me show you an example. So our idea is first to find circuit transformations like these, and then use these transformations to optimize the circuit like the circuit below. So we can see that there are 2 H gates with a C0 gate, and then we can apply this transformation that we flip this C0 gate and move the 2 H gate to the right. And then we can eliminate these 2 pairs of adjacent H gates. So there's only 1 C0 gate at the end. So this is the overview of the Quartz system. So we take as input a gate set, we have a transformation generator to generate some transformations, and feed it into the circuit optimizer, which optimizes the input quantum circuit. Now let's dive into the transformation generator. So the problem is we want to find all valid transformations with N gate and Q qubits. But there can be a huge number of circuits. For example, there are 50 million circuits to consider in one experiment in our evaluation. But with an algorithm called RepGen, we are able to only consider 200,000 circuits. In RepGen, we generate circuits and verify equivalences iteratively on the number of gates. So in each iteration, we have our equivalence verifier that partitions circuits into equivalence classes. And for each equivalence class, we maintain a representative. And then our circuit generator only extends representatives. And it also further ignores some circuits, which due to time limit, I won't cover all the details. So now let's look at an example. So about how we generate equivalences. So this is a 2-qubit empty circuit. And at the beginning, we can generate all the 1-gate circuits with 2 qubits. And then we can extend them to generate two-gate circuit. For example, with this H gate, we can generate, we can put an H gate here, or put the H gate on the second qubit. And we can generate a lot of circuits and so on. So after generating all the two-gate circuits, we go to our equivalence verifier, which tells us, oh, actually the circuit with two adjacent H gates, they are equivalent to the empty circuit. And so does these two CNOT gates in the same direction. So we group them into the one equivalence class. And so here, only the red gates are the representatives. And so most of them, so the circuit on the right, they are grouped into a singleton equivalence class. And the three circuits on the left, they are one equivalence class. Then go back to the circuit generator to generate three-gate circuits. And we only generate circuits from the representatives. So for example, we have circuits like these. And notice that, so among them, the green circuit is actually redundant. Why is that? Because there's a component, so the green part is two CNOT in the same direction, which is not a representative. So actually, we can replace it with the representative, which is the empty circuit. And this three-gate circuit will actually become the one-gate circuits with only one CNOT gate. So if we want to know the transformation about the green circuit, we already have them in the, so when we are considering the one CNOT gate circuit. So we don't want to generate this. So similarly, after generating all the three-gate circuits, we go to our equivalence verifier, which tells us, oh, actually these two are equivalent, so we group them together. And these two are equivalent, so we group them together. So how do we know that we've got all transformations? We have a theorem in our paper that the transformations generated by RepGen subsume all value transformations of circuits with n gates and q qubits. So by subsume, so for example, if we have these two pairs of equivalences, then we can subsume this transformation as shown in the previous optimization example. And so with RepGen, we don't need to consider the all 50 million circuits, and we only generate 200,000 circuits, and it subsumes all value transformations. So now let's go to the equivalence verifier. There's actually a challenge that quantum gates can contain parameters. For example, this is an example. So to deal with this, we use random testing to prune most of the non-equivalent pairs. And for each pair of circuit that passed random testing, we compute a symbolic matrix and use an SMT solver to verify, where in our experiment we use C3. So for example, the circuit above, the corresponding matrix representation is, so for all parameters θ1 and θ2, we want to verify that the product of these two matrices is equal to the matrix on the right. Now let's revisit the overview. So we have an iterative approach, so loop from the number of gates j from 1 to n to get NQ complete transformations. And there are some further transformation pruning, which I won't cover due to time limit. And after that, we feed the transformation into the circuit optimizer to optimize the circuit. So the circuit optimizer does a cost-based backtracking search. And we need to apply some transformations that do not reduce gate count before applying transformations that reduce gate count. So for example, in this case, we need to flip the CNOT gate and move the 2H gate to the left, and do this transformation 3 times. So do it again, and do it again. And then we can eliminate the 2 adjacent H gates. So yeah, this is the difference with the previous approaches that greatly transform the circuit towards fewer gates. And now let's look at some end-to-end evaluation. So this is a geometry mean reduction on the number of gates on benchmark of 26 circuits, so higher is better. For each gate set, we pick NQ, generate NQ complete EC transformations, and optimize each circuit with the generated transformations. So Quartz achieve on-par performance with NAMS optimizer on NAMS gate set, and outperform the best existing optimizers on IBM gate set and Rigetti gate set. It's worth mentioning that NAMS optimizer contains many manually designed transformations, and Quartz is able to automatically generate them to match the performance. So you may want to ask the question, so how to choose N and Q in the NQ completeness? So let's look at this figure. This do the geometry mean reduction on the number of gates on the benchmark of 26 circuits, so higher is better. Generally, the larger N and Q are, the more equivalencies are covered, and the better the optimization effect is. However, if N or Q is too large, we will get too many transformations, and the optimizer will choke. So we have a sweet spot at Q equals 3 and N equals 6. There are 56,000 transformations in total, and it takes less than 30 minutes to generate. But if we just increase N by 1, that is when Q equals 3 and N equals 7, there are 380,000 transformations, and it takes 3 hours to generate. You may think that 3 hours is a long time, but notice that we have search timeout of 24 hours. So it's the optimizer that chokes on Q equals 3 and N equals 7 and cannot finish optimizing within 24 hours. So in conclusion, we have presented Quartz, which is a quantum circuit superoptimizer that automatically generates and verifies symbolic circuit transformations. So it's universal that it can be applied on any gate set. It requires less engineering effort, and it leads to better performance, and also provides formal verification. And it is available on GitHub. So thank you for listening, and I'm happy to take any questions.
Thank you so much for the talk. I was just curious about the previous slide, if you mind going back that one. I guess since this is like situational to a specific like orientation of the like gates when you start out, when you find N and Q, so like would you have to compute like all these optimization for any situation, or is there like a method to choose N and Q like for any situation at all? I don't know if that makes sense. I can.
Well, so this is true to choose NQ for NQ completeness. So which is so we generate the NQ complete transformations beforehand, so before optimizing. So this is a pre-processing step.
Okay.
Yeah.
Okay. Thank you so much.
Super cool work. I have a question. I didn't understand what the 24-hour timeout meant. Was that the time to actually optimize a program was up to 24 hours? Because you said 3 hours to generate. I just wasn't sure what that part
Yes. Yeah. So the search timeout 24 hours is for each circuit. We let the optimizer to run 24 hours for that.
And is the reason that it needs to run that long because you have so many transformations and it's just trying them all out?
Yeah, kind of. So if you set the search timeout, for example, to only a few minutes, the chart will, the figure will be kind of different in that. So the N equals 6, Q equals 3 will, maybe it will also choke, so you need a smaller transformation set.
Okay, thanks.
So from my limited understanding of quantum computation, I understand that sometimes certain circuits are preferred over others because they can be run in parallel. Is this something that you considered during your project for the optimization?
Oh, so do you mean so optimize based on the circuit depths?
Um,
or
Not quite, because like sometimes you have to run a certain gate before the other, so certain representations of the same functionality can be run in parallel based on how you construct the circuit.
So, sorry, I'm not really sure. So what do you mean by parallel?
Like you can run separate parts of the circuit separately at the same time, and there's no interdependency on separate. Like on the first 2 qubits, you could be running a certain pair of gates, and then on the second 2, you could be running a certain set of gates at the same time.
This might be a very interesting future direction. So in this work, we only optimize a single circuit. We didn't consider the separating this. Yeah.
Hi, I was wondering how the technique of super optimization would handle more fine-grained cost models, right? Is it true that you're assuming in this model that all gates take an equal amount of time to execute? And if so, would a cost model in which you could actually have that information in there, would the technique be able to handle such a cost model?
Oh yeah, so the cost model, yeah, in this paper we take all gates to be the same because the previous benchmark, so they compare the gate count, so the total number of gates. And if we have more understanding of which gate can take longer time or higher or lower error rate than the other, then we can design a better cost model for that. So and it's just change the cost in the cost-based backtracking search. I think it will still work.
This may be too similar to the prior couple of questions, but in which case you can say I basically have the same answer. But for classical circuit optimization, and by the way, I think this is a great domain for super optimization, so thank you for this work. For classic circuit optimization, we generally care about the depth of the circuit and the number of gates, and we can change parameters like how much fan in or fan out we have. But it seems there are other things we care about for quantum circuits related to robustness, related to the difficulty of having the same number of gates too many times. We may, unlike in classical circuits, have some predisposition towards knowing something about our inputs, right? We may not need to work correctly for all possible, exponential number of inputs. Do you have any thoughts on those dimensions of kind of changing the cost function?
Well, yeah, sure. Actually designed. So yeah, so there's still so many work to do on the cost function part. So yeah, yeah. Thank you.
All right. Any more questions before we? Okay. Last one.
Hello, interesting talk. Do you know about the ZX calculus from the group in Oxford?
Do you say ZX calculus or?
Yes, ZX calculus, yes. Because it is also used to optimize the circuit, and I wonder if it can be combined with your approach.
Yeah, I've heard of it, although not very familiar, but I think
by Kissinger and Bob Kirk.
Yeah, maybe I'm not sure if one difference we are finding symbolic transformations that works for all parameters, but I'm not sure if they also support so for all for all parameters, so a gate with parameters, they're the equivalences. Yeah.
Thanks for the lively discussion, everyone. We will move on to the next talk.